you already know the delta, so now we know the n, we know the delta, we know the S1, and we know the N1, inverse. So you just multiply those in MATLAB, and out will come your stiffness matrix for the first element. Okay, make sure, notice the units on this. You can stare at those, what sections have what units and why. Okay, but if you provide this on an exam or something, you need your units. Okay. All right, so that's the stiffness matrix of element 1. And what we do is we go back and do the same thing for for all the other elements. We have an L vector that points there, define N1, N2, N3, and do the same thing. And then point there and point there. You do all that, find all those stiffness, K1, K2, K3, and K4, and then you would add them all together, and you would get this twist wrench stiffness matrix. This is the stiffness matrix that relates twists and wrenches for the entire parallel system there. Okay, and it is this. And please go check me at home, do the math, let me know if you get the same matrix with the same units. Okay, and another thing you'll notice is we're assuming for this that the stages are infinitely rigid. We're not taking into account their shape, we're not taking into account their size, we're not taking into account what material. This is completely independent of the stages, or the rigid bodies, and has everything to do with just the wire flexures. So only information when in the stiffness matrix pertain to the flexible elements, which makes sense, that's what it would. With our assumption here that the rigid bodies are perfectly rigid, and the elements are what to form and are the springs, essentially. Okay, and therefore provide the stiffness. Okay, so one other just note here is once you have a system's stiffness matrix, KTW, then if you say I wanted to load this stage with some wrench, maybe a pure force wrench right there, okay, and say I define that with respect to the global coordinate system, that wrench. Well, what I could do is I could take that wrench and I would invert this stiffness. So I'd take KTW raised to the -1 and times it by that wrench, and it would tell me how it would spit out a twist, displacement twist, that would tell me how this stage would move, and it would be defined with respect to that global coordinate system. So the top 3 components of that resulting twist vector would tell me the 3 rotations of this stage, of that point on this stage with respect to this global coordinate system, and the last 3 components of that twist vector would tell me the 3 displacements of that point on the stage with respect to this global coordinate system. Okay, and it wouldn't, if this global coordinate system were down here or anywhere, it would be telling me the 3 rotations, 3 translations of wherever you put it. I conveniently put it up on the top here though, because that's probably a point you care about and makes the math easier, right? Okay, so. And by the way, if you did a displacement load on it, you wanted to put a displacement twist on it, say you did 3 rotations there and 3 translations there, and you slap those together in a twist vector, then you could just times that by KTW. So KTW times T, and then out would come the wrench, the load that would need to be put on that stage, defined with respect to this global coordinate system to move it that way. Okay, so you can literally use this just like F equals KX. And just like F times 1 over K equals X, right? So you can use this just like that, so that you can see how you can displace it or load it and see how it displaces. Okay. All right. So that's very powerful stuff. Okay. Now let's talk about mass matrix. Okay, because we didn't consider at all the mass of this of any of this system. Okay. So. And so what we're going to do is we're going to build a mass matrix for this stage. We don't need a mass matrix for the ground because it's not ever moving. It has no inertia. It's not going to contribute to anything in the system. And what we're also going to do is we're going to assume that there's no mass in the flexible elements. They have all the stiffness, and the stages have all the mass, which is fairly reasonable because you can see here that these guys have relatively little mass compared to the big bulky stage. And so they're not going to have a whole lot of inertia. And so we're just going to assume these guys have no mass, they have all the stiffness, and we're going to assume this stage up here has all the mass and no stiffness, it's infinitely rigid. Okay? Those are the assumptions of this approach, but there's little tricks you can do with the approach to consider the mass, some of the mass of these elements, and consider some of the compliance of the stage. Okay, so there's more accurate approximations of this theory that are a little beyond the scope of this, but I'll hint to them. Okay, but first of all, let's talk about how we describe the mass of this stage. Okay, and by the way, why do we care about finding a mass matrix? Well, it matters very much to dynamics, right? If you're doing if you want to find the natural frequencies, or if you want to dynamically load a stage, with some appreciable speed, then you need to consider both the mass and the stiffness. Okay, so how do we do this mass of this stage? Well, first you need to find the center of mass. Okay, so of course the mass of this stage is just the volume of the stage times that density of whatever material it's made of. That's the mass of it. But where is the center of mass? Well, the general equation to find the center of mass with respect to this global coordinate system down here is the triple integral of vector, the points from this global coordinate system defined with respect to these coordinates, right, to various locations on the stage, okay, times the density times delta x, delta y, delta z, which is an infinitesimal increment of volume. So you're basically taking rho dx, dy, dz is basically dm, it's an infinitesimal chunk of mass, times a vector that points to the center of that chunk of mass, right, and then you integrate, you add it all up over the entire stage, and then you divide it by the mass of the entire stage, which is rho times the volume of the stage. Okay, and so that will then point to the center of mass of that stage. Okay, and if it's just a simple, extruded rectangle or some simple shape, this is an extruded square actually that I'm showing here. Then it's very easy. You don't even need to calculate it. You know, as long as the density is uniform, you know exactly where the center of mass is. So no need to even calculate it for simple stage shapes. But if you ever have a complex stage, you can use this, okay, and do integration. Okay, so every body, every stage has a mass, rho times v, and it has a center of mass. And we can now calculate where that center of mass is. And that center of mass is essentially the location where that mass manifests itself, or it's kind of an equivalent location. Like if you were going to model this as a point mass, you'd model it at that point. Okay, so that's kind of a way to think about center of mass. Okay, okay. So now what you would do is, but again, when you're considering inertia of a body, you don't just consider its mass, right? That's kind of the linear component of inertia. What you also need to consider is the angular mass, or kind of the mass moment of inertias. Okay, so that's if you're actually rotating the body, then it's got an we're talking, when I say linear, I mean F equals ma. Those are all linear things. Force is linear, acceleration is linear, and you times it by mass, right? And it would be, by the way, the acceleration at the center of mass. Is what acceleration used for F equals ma, Newton's equation, right? But when you're talking angular things like torque equals mass moment of inertia times angular acceleration, those are all angular rotational things. And now it's not just mass. You have to use mass moment of inertia, which, of course, hopefully you'll know is the integral of r squared times dm. Right, you take the vector that points to a spot in the body, take it. Well, I'm about to give it to you here in a second, but anyway, this is a review of high school or early college math, right? How you find mass moment of inertia. Okay, but I've taught you the mass of the stage is rho times v. The center of mass is right in the center. That can be found by that thing. But now, how do you find what do you do with mass moment of inertia? Well, excuse me. I'll teach you a principle. I'm not going to go too deep into it because it's actually fairly complicated and beyond the scope of this, and you don't need to understand it all to do simple stages. But you could pick any point of a stage or a body, give it a coordinate system, And to define that body's angular mass moment of inertia, basically, you would do a 3x3 inertia tensor, okay? And for every point that's located, as you move that coordinate system, you will change the components in that tensor. And if you find there's always a particular direction at a particular point where that tensor will be a diagonal tensor, and all the components are 0 except along the diagonal. And that's called, that corresponds with directions that are called principal directions, okay? Okay, so the point we're most interested in, though, is the center of mass. And so what you do is you define a new coordinate system, x, y, and z. And it's important you define that coordinate system so that those are the principal directions. So for that point at the center of mass, you want to place your coordinate system there, and you could angle those in any weird cockeyed way, and you'd get a mass moment of inertia tensor. But if you locate them along the principal directions, okay, which are usually easy to intuit and find, and for a rectangle, prism is just obviously the directions that are perpendicular to all the flat faces, then they will be the principal directions, and the inertia tensor goes to just a diagonal matrix. So it's all 0 everywhere except the middle, the diagonal 3 will be non-zero. Okay, and those are the ones we can easily calculate. Okay, so I'm teaching you the systematic steps to find a mass matrix, and step 1 is find the mass of the system. Step 2 is find the center of mass of the system. Step 3 is define a coordinate system, a new coordinate system at that center of mass, and orient them in principal directions. Okay, this is kind of like how we found principal directions of the elements. We put them going along the axis, going into the stage, and then perpendicular to the flat faces. You kind of do the same thing with the stage. Okay. And like I said, for rectangular prisms, for other things, that's easy to intuit. Okay, in this case, it's just like that. And again, x could have pointed this way, and y could have pointed that way. Z, we could have even pointed z in any direction. We just make sure they follow the right-hand rule, that x cross y equals z. Right? You do the right-hand rule, and you make sure all 3 point perpendicular. Okay. All right, and then we can find the moments of inertia. By the way, though, you might be saying, well, what if I want to use? What if I have a stage that's very complicated? What if it's just some bizarre convex or concave polygon that's extruded? What if it's not clear where the principal axes are? That's what's beyond the scope of this course. Our lab has a tool that you can, for any stage that consists of multiple strangely oriented or arbitrarily oriented, I'll say, polygon extrusions of any kind of polygon geometry. It'll calculate the mass, the center of mass, and the principal axis of that stage, and will essentially generate the mass matrix for it. But for now, you're not expected to know that theory. I'm just going to assume stages are easy and are pretty easy rectangular prisms, and the principal axes that you want to define in this step are kind of intuitive, right? Okay, so then what you do is, once you've picked those principal axes that go through the center of mass, you're going to define an n1, n2, and n3 unit vectors. And again, have n1 correspond with x prime, n2 correspond with y prime, and n3 correspond with z prime. And make sure their magnitudes are 1, and make sure they're defined with respect to the global coordinate system. Okay, so again, you have an L, you have an n1, n2, and n3. Okay? Okay, so now use the transformation matrix to calculate the rotations and translations of the stage about the new coordinate system. So again, you're probably smelling a transformation matrix. And again, please watch lecture 2. It's one of the most confusing principles in this course, is understanding the derivation of that and how it works. But the bottom line is, here's the matrix. If you do it for this L and this N1, N2, N3, if you take that and you invert it, so here it is inverse, and you times it by some displacement twist vector that's defined with respect to this global coordinate system. So again, you would imagine this stage as well as this point stuck to the stage, twisting, screwing about this axis for any pitch, whatever they specify, right? Where the top three components of the three rotations at this point and the bottom three components of the three translations at this point with respect to that global coordinate system. If you had that and you multiply by the inverse of this for this L, N1, N2, and N3, then you would get the three rotations and the three translations of this stage with respect to this new local coordinate system centered at the center of mass and in the principal directions of the stage. Okay? So for that twist, as the stage moves, you now know the three rotations, three translations of that point with respect to the new coordinate system. Okay? So that's what that is. Okay? And now you might say, okay, now let's find the mass moments of inertia about those principal axes. Okay? Because that's not beyond the scope of this course. We can find those from simple high school math. Okay? Okay, so let's find Ix prime, okay, and Iy prime and Iz prime. Okay, so what's the angular kind of mass moment of inertia if you rotate this stage around these axes is kind of what we're talking about. What's the thing that if you times torque x equals Ix times alpha x, right? With primes above them all. That's what we're trying to find here. What's the mass moments of inertia? Well, here's what you learned in high school. Say you have a stage, okay, it's a rectangular prism, and you have x, y, and z coordinate systems in the center of it. Okay, and let's take, say you want to find the mass moment of inertia about the axis that is, parallel to x and is collinear with the x-axis here. Say you're rotating around the x-axis. Okay. Well, what you would do is you would take a vector u. It's not a unit vector. It's just a vector, and it points to every point with a direction that's perpendicular to that axis, which is why its x component is 0 for this case. But it points to every point in the body. Okay. And if you do that, if you dot product it with itself, then what you do is you take the magnitude, the length of it times the magnitude times cosine 0, which is 1. And you basically take this distance, so the magnitude of that squared, and then you times it by rho dx dy dz, which is this little volume increment, times rho, which is a little mass increment. And now you get basically what I told you, which is the integral of, some distance. I said r squared times dm previously, right? But in this case, we're using u dot u, which is the magnitude of u squared times the little mass increment. We're going to sum it up over this entire thing about the x-axis here, and we'll have Ix, the mass moment of inertia about x, okay, which is an axis that passes through the center of mass and is collinear with the x-axis, okay? All right, well, let's actually do this integral. If you dot product these, you line up corresponding components, multiply and out, so you have y squared plus z squared. That right there in the parentheses is the dot product. We're going to pull the rho out, and we're going to integrate. Remember, it's in the center, so we go from negative h over 2 to h over 2, and you can see do the same with the b, do the same with the l, and you're going to integrate. So we'll do the x first, and when we do that, I'm not going to teach integration in this course. I'm assuming you know how to integrate. Okay, check my math, you get from there to there. Now we're going to do along the y direction. We're going to integrate that. Check my math, you get there, and then you're going to do along the z direction, and you get there. Okay, and you can simplify this more by recognizing that the volume of this is LBH, and so you can pull it. You can simplify this to this, where we basically have the mass of the stage, rho v. That's the mass of the stage, divided by 12 equals b squared plus h squared. Notice, if you're rotating around this axis, the face that's perpendicular to it is this, and that's where you get the b and the h. So there's nothing physically significant about that other than it's just a nice way to memorize this equation. Okay. And you could see if you're doing the mass moment of inertia about the y-axis, you could do all the same math, and now the face that's perpendicular to this is LH, and so that's why you get L squared plus H squared. And if you do the same thing about Z for IZ, the face it's perpendicular to would be, BL. So there's B and L squared in there. Okay, so it's easy to remember. Okay, this would be a good equations to memorize. Okay, so now you can find the mass moment of inertia about a rectangular prism, right, about an axis that goes through the center of mass and is in the principal axis directions, okay, which are orthogonal to the square's face. Okay? All right, and so now let's take an axis A, and let's say, well, you know, what if we want to find the mass moment of inertia that doesn't go through the center of mass, that's not collinear with one of these nice principal axis directions? What if we want to find some off-axis thing, like about an axis A, which is parallel to the x-axis, but obviously does not go through the center of mass? Well, then you use the parallel axis theorem. Okay? Or, I mean, you could use the same approach as before, right? This is the same equation. You would still take u, which is still, you know, the x component is 0, because it's parallel, you know, it's coming out of x, where it's 0, y, z, basically a vector that points perpendicular to this axis, okay, that points to everything in there, and times it by rho dx dy dz, and you would get your, you know, you would get your mass moment of inertia about axis A, so it'd be IA. You could do that, but that if you did that, it would be a lot of work, and it would be kind of a pain. And you would find that you would more simply be able to just use the parallel axis theorem. Okay, so what is the parallel axis theorem? Well, it's easily derived, but this is the theorem. You probably learned it in high school physics or in freshman year mechanics class. Okay, so this one is if you take, you know, it's called the parallel axis theorem because it's got to be an axis. You use it to find the mass moment of inertia about an axis that's parallel to an axis through the center of mass. So say you have, say you already knew Ix, the mass moment of inertia through the center of mass about the x-axis here. That's Ix, so you know that. But then you add it to the shortest distance between this axis, right, and the x-axis here, which is d squared times the mass of the stage, rho times v. So notice it's always some distance squared plus, you know, times some mass, okay? And so, of course, they're the same units, and so you can add them, and you have IA, and that's what you get, okay? So if you know this equation by heart, then you can find, you know, the mass moment of inertia about different axes that are parallel to axes that go through the center of mass, okay? So it's a valuable thing, okay? Okay, so that's a little note there. Okay, so let's then do this. Let's find these mass moments of inertia. Okay, let's find Ix prime, Iy prime, and Iz prime. Okay, so here's the stage. Let's say this is B, that's L, and this is H. Okay, and you know, okay. And so we would know Ix prime, Iy prime, Iz prime are these different things. You can look at those. Remember, you can memorize those equations. And like I said, I like to think if you're going out of x, find the face that's perpendicular to it and take its two parameters and square those. That's a nice way to remember it. But anyway, that's what they are. And so we found them. Okay? Now that we know those, and again, we didn't have to use the parallel axis theorem for this at all. These are just very basic mass moments of inertia about axes that go through the center of mass and are axes that are principal axes of a rectangular prism. Okay, and so now what you do is you make what's called an inertia matrix. Okay, where that's what IN stands for. It's a 6 by 6 matrix. It is a diagonal matrix like this. Okay, so if you type in diag and do this in MATLAB, you'll see it'll populate a 6 by 6 matrix where all the components are 0, but the diagonal components going from 1, 1, 2, 2, 3, 3, 4, 4, 5, all the way down to 6, 6 are these components, okay? Now you'll notice the first 3 components are the angular inertial ones, the mass that's mass moment of inertia about the principal directions. And you'll notice the last 3 are just the mass of the stage, and so it's kind of the linear components, okay? Now remember, if you hadn't picked this coordinate system up here to be corresponding to the principal axis of that stage at its center of mass, then it actually would be, it would still be a 6 by 6 matrix, but the top quadrant of that matrix, the 3 by 3 matrix, the top left right, or sorry, the top left corner of that 6 by 6 matrix would not, they would all be populated with non-zero values, okay? Because this was oriented with respect to the principal axes, this can be a purely diagonal matrix, okay? But again, that's outside the scope of the course. If you just kind of, again, here's the process that all you need to know for this course, okay? Okay, so you find the mass of the stage, rho times v. Then you find the center of mass of the stage. It's usually by inspection, okay? You got that. Now put a coordinate system at that stage, at the center of mass, and orient it so it's obviously nice and clean. And 99% of the time for simple stages, you'll have found that you'll be able to intuit the principal axes, okay? For rectangular prism, make sure they are perpendicular to all the faces and follow the right-hand rule, right? Then define, your L, N1, N2, and 3 vectors and make a transformation matrix. Find the inverse and the norm one of that, and then find an inertia matrix, okay, where you find the mass moments of inertia about the principal axis you found, and then plug in your mass there. And finally, then what you do. Now what do you do with that? Well, I'm going to prove what you do with it. So remember, if we take this twist, times it by n inverse, you get t prime, which is basically the 3 rotations, 3 displacements of that point on the stage with respect to this local coordinate system that we defined, okay, caused by this stage twisting about this green axis here, okay. And if you take the derivative of these, remember the twists we're going with are displacement twists, okay. They're basically normal twists, which are velocities times delta t, which are just infinitesimal increments. These are infinitesimal increments, okay? Just to be nice and clean, so up to this point we've been calling those such displacement twists just t. Okay, we're going to start calling t dot is a convention. Usually that means take the derivative of something with respect to time, right? And what we're doing is we're basically just dividing all these by delta t. So these are kind of the traditional twists. Okay, we're going to write those traditional twists, but in this lecture we're going to call traditional twist t dot, okay, and displacement twist just t. And then if you take the derivative of them again with respect to time, t double dot, okay, then what you get are an acceleration twist, okay, where the first 3 are angular acceleration, last 3 are linear accelerations, and that's notice there's a transpose there, so it's a 6 by 1 vector. It's t double dot prime equals n inverse times t double dot, okay? Where t double dot is the 3 rotations and displacements at this point, and t double dot prime is the 3 rotations and displacements of that thing, okay? But again, they're the accelerations. So 3 angular accelerations, 3 linear accelerations of that point on the stage as it twists about that with a certain acceleration twist, okay? Okay, so there's that, and then you can see that if you take that, so again, we're just going to look at this, zip it up there, okay, if we take that, times that by the inertia matrix, remember, this equals the 3 angular accelerations and the 3 linear accelerations at that point. If you times that by this inertia matrix, remember that it was just a diagonal matrix. We're just lining up alpha x times ix equals tau x, okay, but they're in the prime coordinate system. Then you get all these taus and forces, okay. And notice the last 3 is just the mass, times the linear acceleration of the center of mass equals the force at the center of mass there, okay. Okay, so hopefully you can see how tau double prime equals n inverse times inertia matrix equals this. Again, this almost looks like a wrench. Let's times it by this delta matrix, the 6 by 6 matrix we invented essentially to switch the location of the taus and the forces. So we get the linear components first and the taus later. That just is nice bookkeeping in math. And then again, you can multiply these guys by the n, the transformation matrix, again, not inverted. So you take all this, times it by this not inverted, and it will linearly combine all these together as if it's with respect to the global coordinate system and take a wrench back to the global coordinate system. So this equation essentially is F